Just a tap. All right, let me bring it out more. Hello. Please let me know if you can hear me. Oh, too far.
Yes, I could hear you, sir.
All right, Esmeralda, did you talk to me? Because if you did, I couldn't hear you.
Yes, sir.
All right, so I need to find out where my speakers have gone to.
Morning.
Hi, how you doing this morning? Okay, Esmeralda, try again. Esmeralda, can you talk to me again?
Yes. Good morning.
Okay, still not hearing me. And maybe, just maybe. Try again.
Good morning, sir.
Try button. Yeah, let's turn all the way up. Not letting me hear you. Let's try again. Well, talk to me now.
Good morning, sir.
There, I can hear you, but now you're on the speakers on the computer, which is not loud enough. I prefer the disembodied voice from the ceiling because those speakers are loud. Let me try again, see if I can get them to work. Okay, try now.
Good morning.
Well, I'm gonna cuss really bad words here in a minute, because it's not doing what it's supposed to. All right, try this way. It's giving me 4 options for speakers, and so I'm trying all of them. And the one that's supposed to work isn't working. So if we could talk again. Just say hi. Oh, and don't forget to put your name in the chat. All right. Esmeralda or Sebastian, either one of you say something.
Good morning, sir.
Oh, that's, yeah, there we go. Thank you.
Can you hear me?
Yes.
All right.
So I don't know which speakers are actually playing, but yeah. Yeah, put first name and last name, please. Although there's not another Sebastian in the class, I just like it to be both names. And find out where we are. Haven't gotten that far. Have we gotten to chapter 7?
Maybe. I can't remember.
Oh yeah, we did inverse functions. Did we start with the trig functions, I mean equations. I think we did that. I think we were gonna start 7.4, weren't we? Yeah, we were gonna start 7.4. These lovely bastards. Okay. Oh, you're kidding me. Someone puts with the settings in this lovely computer. There we go.
I never noticed your earring,
What?
right? You have an earring, or what is that?
Yeah. I never take it off.
How long have you had it for?
Well, this earring has been, I don't know. The last time we went to New Mexico, and I don't remember when that is. Oh, actually, I do. It was in 2014.
Wow, you've had it on since then.
Well, but I had my ears pierced when I was working at Mark Twain Middle School. Actually, the summer before I started working there. And then, so I always have it in my ear, but when I worked at Poteet Middle School, Poteet High School, school policy is that males were not allowed to have pierced earrings or to wear them. And so I get to school, I had to pull it out, or I pull it out on my way down and I put it back in when I left campus. So sometimes I would forget to take it out. And the kids in my first period class said, "Mr. Reed, you still have your earring?" So, anyway, fun times were had my own. Oh, damn, I got busy talking. I didn't change the setting. Okay. Combine, oh no, I want combine never. There we go. Then I just push a button down here. And I have control over it. This device. Make sure it's plugged into the right place. Turn it on, make sure it works. Okay. Oh, yeah. So here's this. Oh, 5 minutes into class, okay.
Oh, thank you.
Sanitize this between people using it. I went to my dentist yesterday morning and they have a bowl full of pens that can pull out and then a tray full of pens that once they're used, put them there.
It's amazing.
It kind of rips it apart too. Borrow some tape from somebody's office and just tape it together. Okay, I'm pretty sure this is where we left off last time. For some bizarre reason, this particular class has resparked my made me revisit why I love mathematics so much. And this is one of them, using trig identities. When I was in high school, we didn't have pre-calculus. We had trigonometry, which was a semester course, half a year, and analytical geometry and elementary analysis. And so to get into high school calculus, you had to take the trig and the elementary and the analytical geometry, which is basically what pre-calc is. Except in analytical geometry, we did more in that class than we do in this one. And oh, I really love that class. But doing trig identities, our teacher, Mrs. Hay, who everybody hated except for me, we were allowed to use a 3x5 index card and write all the trig identities, the standard trig identities on it, and we could use that on a test. Well, I went to make out my thing, and I went, I know all of these, so I didn't have a 3x5 card. I just, I loved it. Anyway, needless to say, I made an A in that class. I just had so much fun in it. I sat on an outside row, right by the door to go out. There was one person behind me, and then the three beside me on this side, the guy in front of me, and they all passed because they cheated off my speed. So, okay, so we're going to use algebra to simplify algebraic expressions and establish identities. Establish identities is what people usually think of when doing trig identities. Okay. Identically equal, I'm not being able to speak today. Identity and conditional equation. So we're going to define that, or those things. Two functions f and g are equally equal if f of g equals g of x, f of x equals g of x for every value of x from which both functions are defined. Such equations are referred to as identity because they equal each other. It's like saying 8 equals 8 or 8 equals 3 plus 5. That's identity. 4 plus 4 equals 5 plus 3. They're equal to each other, so it's identity. That's why we call it identity. And we say they're identically equal, or what's that word? They don't have the word there. They are equivalent because they're saying the same thing. An equation that is not an identity is called a conditional equation. That means they're equal only under certain conditions, only when x is this set of values. And that's what we deal with when we're solving equations for x. Those are conditional equations. Like you have 3x plus 3 equals 9. That's a conditional equation because it all depends upon the value you put in for x. So it has a condition that x has to be a certain value or comes from a set of values. All right, so these are identities we've already had. The quotient identities, which tangent is sine over cosine, cotangent is cosine over sine. Cotangent, secant, and cosecant are the reciprocal of sine, cosine, and tangent. So we've already dealt with these. We've dealt with the Pythagorean trinity identities. All right, this is the basic one. And I went through the process of finding this one and this one. To find this one, we divide everything by cosine. Sine over sine is tangent. Cosine over cosine is 1. And 1 divided by cosine is secant. And so dividing everything by cosine squared, we get this Pythagorean identity. And then if we go back, instead of dividing through by cosine, if we divide through by sine, then we have sine over sine, which is the 1. And I typically write this one as 1 plus cotangent squared. But it doesn't matter because of the commutative property of addition. And then cosine over sine is cotangent. And then 1 over sine is cosecant. And so you build these two from this one. So this is the only one you really need to know. And then just knowing the reciprocal and the quotient identities, you can build the other two. Now the even and odd nature, sine is odd. So sine of the negative is the negative of the sine. Cosecant is also an odd function. Tangent and cotangent are odd functions. Cosine and secant are even functions. So the cosine of the negative 45 degrees is the same as the cosine of 45 degrees. And the cosine of 3 pi over 2 is the same as the cosine of a negative 3 pi over 2. Wait a second. Yeah, it's still 0. Okay. Right. Now, 4 basic techniques are used to establish identities. You rewrite. All right, so what we're talking about identities is you have an expression equal to something. You have an expression of sine, cosine, cosecant, and all that, and it equals another expression of trig functions. And you're going to rewrite one side so it looks like the other side. And that's using trig identities. You're using substitution based on the trig identities to get there. Okay. Everybody online, make sure that you have signed in. I should have stated that earlier, and be sure you pin my screen because it makes it big and things show up better. Okay, so rewriting a trig expression in terms of sine and cosine only. So that's one technique. Multiplying the numerator and denominator by a ratio by a well-chosen 1. Remember, we're always multiplying by 1. It's just, what does the 1 look like? Sine over sine, cosine over cosine, tangent squared over tangent squared. What is that one I'm going to use to multiply with? And then writing sums of trig ratios as a single ratio. And so you find the common denominator and add the numerators or subtract the numerators. And then factoring. If you can factor, it sometimes makes it an easier problem to solve. So simplify this by rewriting each trigonomic function in terms of sine and cosine numbers. Okay. So we have tangent theta and we have secant theta. Well, I'm going to split this off into tangent theta times 1 over secant theta. Okay. I can do that, right? 5/2 is the same thing as 5 times 1/2. And that's all I'm doing. Well, to write tangent in terms of sine and cosine, well, that's easy. That's easy. That is the sine of theta divided by the cosine of theta. That's a basic trig identity that should reside in your head permanently for the rest of your life. It should be there because you've been dealing with it for a long time. And 1 over secant, well, that's a reciprocal function of cosine. So this is times cosine. Oh, cosine in the numerator, cosine in the denominator, guess what? Those go to 1. So this is just sine. Tangent divided by secant is just sine of theta. Cool. So it's been really simplified. So if I know what theta is, then I just take the sine of it. Okay. Oh. Damn. You want to show that this equals this. All right. So I'm going to manipulate this till it looks like that. And they suggest by multiplying by 1 plus cosine theta. There's a thing we use all the time in mathematics. We use it all the time. And that is a minus b times a plus b equals a squared plus minus b squared. When you multiply the sum and difference of the same two terms, you get the difference of the square of those two terms. So here I have two terms, 1 and cosine theta. So I have the difference. So if I multiply by the sum of those same two things, it's like squaring the first term, subtracting, squaring the second term. So if I take, I'm gonna have to end up erasing this. Let me do it over here. So I have sine theta divided by 1 minus cosine theta. And I'm going to multiply by 1 plus cosine theta divided by 1 plus cosine theta. I'm dividing by my well-chosen 1. So my denominator becomes 1 minus cosine squared theta, and my numerator is sine times 1 plus cosine theta. But what does 1 minus cosine squared theta equal? Think of your Pythagorean theorem. Think of the Pythagorean identities. The very first one is sine squared plus cosine squared equals 1. Well, if I subtract cosine from both sides, don't I get this? So this equals sine squared. So now my denominator is sine squared. So now I have sine theta times 1 plus cosine theta divided by sine squared theta. And look at my numerator. I have the 1 plus cosine now. But I have sine squared down here, but luckily I have a sine up here. So now I can reduce this part of the fraction. This goes to 1, and one of these signs go away with it. And so that's going to be sine to the first. So now this is 1 plus cosine theta divided by sine theta. I get so excited, I'm out of breath. Okay. Boom, did it. And we multiplied by 1, use the Pythagorean trig identity, and reduce the fractions. We reduce fractions all the time in this class. Okay, so yeah. Understanding how fractions work and being able to manipulate fractions. Understanding how to simplify a complex fraction, really, you use those skills, those thinking skills, not necessarily those direct skills, but you use those thinking skills all the time. This is puzzle play, finding the pieces of puzzles that fit what we're dealing with. So I have more puzzle pieces that I can use here, but so which ones do I need to use? And that's what's undaunting about this is, well, what can I use here? What can I do here? Well, that's where you start thinking about things. What can I do? Well, I can multiply by 1. I can use trig identities to change the expressions to look like something else. Simplify this by factoring. Well, we just went over about what this is, right? A minus B times A plus B equals A squared minus B squared. Well, isn't that what I have here? Is it 1 just 1 squared? So I can factor that numerator. And I can factor this denominator because they both have tangent in them. All right, letter A was sine theta. Because I'm going to erase this now. Because now I need the space. So I can use, so this isn't even trigonometry, this is just algebra. So knowing that to get the difference of two squares, you're multiplying the sum and a difference of the square roots. So the square root of cosine squared is cosine. So I have cosine in both my binomials, and one's going to be plus, the other one's going to be minus, and the square root of 1 is 1. Right? And I can divide tangent out of both of these. So now I have tangent theta times cosine theta plus 1. Right? Because when I divide tangent by tangent, I get 1. It doesn't go away. That's one of the biggest things I had to fight my 14-year-olds over. Freshmen. When you divide a variable by itself, it doesn't disappear. It doesn't go to 0, it goes to 1. Dividing never results in 0. unless you're dividing into 0 is on the numerator. Okay. So now I have cosine plus 1 and cosine plus 1 in the numerator and denominator. So those go to 1. So this is just cosine minus 1 divided by tangent. Can I simplify that more? No. Well, maybe. Oh, yes, I can. Tangent is sine theta over cosine theta. And so here no, it's not going to work out. Yeah. That's not going to simplify it. That's just going to make it more complicated.
I have a question.
Yeah.
What happened to the denominator again?
I factored tangent out.
Okay.
So tangent cosine divided by tangent, the tangents go to 1, just leaves me the cosine. And then tangent divided by tangent is 1. And the tangent is on the outside. Now this next one, all right, you want to get the denominators the same so you can add the numerators. So the only way to make these the same down here is to multiply this one by cosine and multiply this one by sine. So then you have sine u cosine u and sine u cosine u. So you get the same denominator. So I'm multiplying by 1 here, cosine over cosine, and I'm going to multiply by 1 over here, sine over sine. This is something you've done when adding fractions all the time. When you have different fractions, when you have fractions that have different denominators, and they don't have any factors in common, then you just multiply the two together to get the common denominator. And you multiply the numerators appropriately. So my numerator, the first numerator, becomes cosine theta plus times 1 plus sine theta divided by, I always tend to write it sine theta cosine theta, plus, and my numerator is going to be sine theta times, oh nice, cotangent. Oh, it's not theta, it's u. I don't like it that they go to u so much, but that's me. It irritates me. I'd use theta all the time. It's like when they use random algebraic expressions and they start throwing different variables instead of x. It bugs me. Okay. But that's my problem. Sine u times, okay, this is going to be cosine u. And my denominator is going to be sine u cosine u. Okay. The denominators are the same, so I can write it as one happy family. Sine u times cosine u, and in the numerator, since I'm adding, I don't need to worry about parentheses or anything as far as the addition. But what I'm going to do, oh, well, no, I'll do that next. I don't like to do multiple things in each step. So it just the denominator looks exactly, the numerator looks exactly like these things with a plus sign in between, that's all. And if it was minus, then it would be the same thing with a minus sign in between. It's just when we did the distributive property here, we'd have to multiply in with that negative sign as well. And that's what we're going to do next. We're going to do the distributive property. So cosine u times 1 plus sine u gives us, I'm going to write it over here, cosine u plus sine u cosine u, because I multiplied cosine times 1 and cosine times sine. And here I'm going to do sine times cotangent and sine times cosine. So that's going to be plus sine times cotangent u. What's it? It's minus sine u cosine u. So I wrote a theta even though I said u. And it's all being divided by sine u cosine u. Any questions so far? Please don't hesitate to ask questions. Make me stop if I'm going too fast for you. Okay. I know y'all on Zoom may think, or some of y'all may think that I'm ignoring you, but I'm not. It's just y'all aren't on camera, so I can't see your happy faces and or terrified faces, depending on the subject matter at the time. Okay, so right now, I'm gonna look at like terms, because I know I have like terms in the numerator. I have a plus sine u cosine u, and I have a minus sine u cosine u. What happens when I combine those two? Cancel out, yeah, it's like 3 minus 3, it goes to 0. So this goes away with this one. So I'm gonna write the simplified form, but I'm not done yet. Now I have cosine u plus sine u cotangent u divided by sine u cosine.
I have a question.
Yes.
How did you get from the last equation to,
This?
yeah, to over there?
Over there, okay, distributed property, this times
Oh, okay,
one,
just
this times that, this times that,
Okay.
this times that. All right. I know cotangent, is cosine over sine. Cosine over sine. So I'm gonna rewrite this as cos. I think I'm getting out of the picture here. And I'm running out of space, so this goes away. So I'm gonna have cosine u. Is it plus? Yeah. Plus sine u times, and cotangent is cosine over sine. All right, that's one of the quotient identities. So now I have cosine u over sine u, and I'm still dividing by sine u times cosine u. Oh, man. What happens here? I have sine over sine. What's sine over sine? 1. So sine u and sine u, those go to 1. So in the numerator, I just have cosine u plus cosine u divided by sine u cosine u. Well, cosine plus cosine, I have 2 of them. So now this is 2 times cosine u divided by sine u cosine u. Well, now I have cosine divided by cosine. What happens? Boom, they're gone. They go to 1. So now I have 2 divided by sine u. Well, what's 1 over sine? Yes, co what?
Cosine.
No, not cosine. That other one, cosecant.
Cosecant.
Okay. No, that's okay. Where was I? Oh, here. So this is just 2 times cosecant u. There is simplified. This fun fraction down to that. Now we're gonna see if I made mistakes.
That's really fun.
I'm pretty
We
sure. I
did all
did.
that work.
And so, yeah, so they wrote it that way. Well, no, I wouldn't have done it that way, but I would have waited till later. And so, yeah, so they wound up with sine, same way, same deal.
That's how I got the answer.
That's how you got it?
Yeah, that's how I was taught before.
Okay, cool. Yeah, I mean, that's fine. I mean, right here, I could have done this. The denominators are the same, so those can go away. I could have taken away them and that's, so boom, we're done.
Yeah, well, it's the reciprocal identity, right? For the secant, I mean,
Say again?
is it secant equals 1 over cosine, right? That's why the reciprocal identity is called.
Right. So this is the secant, and that's in the denominator. I would use a bigger fraction bar here, but just to show that you have a fraction over a fraction. Not some weird configuration. Right. And this one, they asked you to multiply numerator and denominator by 1 plus cosine. And then did the multiply, and then this equaled sine squared. And those went like that, and so they even did the same notation I did. But I would have put a 1 here where they didn't. To show that this square becomes a 1 because one of those, the sine squared is sine theta times sine theta. So we're just taking one of those away. Okay. And wound up with that, that's when I erased it. And this one, factoring. Where did I do this one? No, I did B over here. And this is,
That's big.
this
Oh, that
is,
one's C.
yeah, this one's C. And so they got to this. No. That one is,
No, that one's
oh, that's the
big.
one I erased, okay.
Yeah.
And so. But that goes away with that. And then we're done with it, I think, yeah. And then the last one is the more complicated one. And we'll see if they take it down to cosecant or they just leave it here. Okay, so multiply both sides, both fractions, one by cosine over cosine, the other one by sine over sine. And wind up with this. Well, they went straight to this. Okay. They skipped writing this and just wrote it as a single fraction. I tend to do that as well. I just didn't do it today. And then looking here, those two go to 0. And this part here, the cotangent u and sine u. And changed cotangent to cosine over sine, so the sines went away. And so now we have two. And then the cosines go away. And yeah, they left it there like that. They left it like this. Because they wanted to leave it in their particular rule for doing these particular problems is leaving it in sine and cosine. But you don't have to. I think this is a simpler than this, but that's me. Okay. Establish the identity that cosecant theta times tangent theta equals secant theta. All right. Cosecant is 1 over sine. And tangent is sine over cosine. Well, sine and sine go to 1. And so that just leaves us 1 over cosine, which is secant. Will you be required to memorize all the basic trig items? No. I'm going to put in files a sheet that has all the trig identities that you could possibly be tested over. In other words, you might use them in the homeworks or on exams. Start with the left side contains more complicated expression. Use the reciprocal identity and a quotient identity. And that's what I did. I used the reciprocal of cosecant and I used the quotient identity for tangent. And so they rewrote it the way I did. And then the sines go to 1. And we're left with 1 over cosine, which is secant. Okay. Yeah, some of them are I consider this one as being easy or trivial. Or this is a more simple trig identity to prove. And so what this is a proof. This is proving that this is secant.
So the identity is 1 over cosine theta, right?
Say again?
The identity is 1
Oh.
over cosine theta.
Yes, this is the reciprocal.
So it's just saying like this is equal to this, right?
Right, that's all they're saying. They're saying this equals this. And this is why. So, and that's what you do when you solve equations. You're doing a proof. Equations are a proof. And so 3x plus 7 equals 13. So you go through, and if I write out how come I can do this, and stating what we're doing here when we do these things is more a formal proof. So the formal proof here would be cosecant equals 1 over sine, so that's what happens here, and tangent is sine over cosine. And so stating those identities is would be the proof, would be part of the formal proof. And so saying you're subtracting 7 from both sides using the subtraction property of equality, which states if you subtract something from both sides of an equation, it remains equal. And then you're going to divide, and so that's the division property of equality. So if you state the property you're using as you're doing it, then that's a formal proof. It's still a proof, even if you don't make it a formal proof. The right side has been reached, so the identity is established. Okay. Oh. I mean, I need it. Is that cosine negative? Is that negative theta there with the cosine? I can't see it, but it looks like it's supposed to be there. There's a faint line here on the.
Oh, yeah, theta's negative
Okay,
for both.
I could have gone over here and looked. Okay. Is that saying it equals 1? Okay. The even and odd nature of identities, sine of negative theta is the negative of sine theta. But please notice they rewrote this as sine of negative theta being squared, because that's what this square means. I'm squaring this. And the cosine squared means I'm squaring this. Well, cosine of a negative is just the cosine of the angle of the positive. So this is just cosine squared theta. Where this is a negative sine theta squared. Because sine of a negative is the negative of the sine. But I'm squaring a negative, which makes it positive. And so there we have sine squared plus cosine squared, which is what? Which is the Pythagorean identity. So we want to prove that, so we proved or established that the sine squared of a negative angle and the cosine squared of the same negative angle also equal 1. And it's a notation issue. That's all this is a notation issue. Because just because I'm squaring this doesn't mean I get the same thing as sine theta squared. But it is. Okay. Factor the numerator. I have 2 terms. I have the square of 2 terms, the difference of the square of 2 terms. Well, that can be factored to the sum and difference of the 2 square roots. So we have sine of negative theta minus the cosine of negative theta times the sine of negative theta plus the cosine of negative theta, all being divided by the sine of negative theta minus the cosine of negative theta. So I wrote an 8. And no clue why I wrote an 8. I just did. Well, here I have sine of negative theta minus the cosine of negative theta in both the numerator and denominator. So these two things go to 1. And that just leaves me the numerator, which is the sine of negative theta plus the cosine of negative theta. Well, the cosine of negative theta is just the cosine of theta. And the sine of negative theta is the negative sine of theta. And using the commutative property, I can switch my negative sign and my cosine and write it the way they have it there, which is cosine theta minus sine theta. What you will notice about trig identities is these, so far, these have been pretty, I don't want to say easy, but they're pretty elementary. Because you just use a couple of algebra facts and some of the identity facts. But you always have a goal in mind. You're always trying to get to what's on the right-hand side or the simpler side. And so I want to take apart things. Here, I notice that I have the difference of 2 squares, so I factored it. And then I notice I have denominator and numerator. I have factors that are the same, so I simplified and got rid of those. And then I used the even odd nature of sine and cosine to rewrite the expression. And then I just use one of the properties of addition, the commutative property, to rewrite it to make it look like what they have. Because technically this is that. But we want it to look like that. And that's what they do here. The left side contains a more complicated expression. So we usually start with a more complicated side. And I didn't do anything with the negative theta until I got closer to the end. But they started with that to begin with. Okay. But they only did it in the numerator. Well, because then you have the difference of 2 squares. You're still going to factor them. Oh, there they used it. Okay. We're still going to factor the numerator, and we still and their way of doing it makes it a little more complicated. Because they simplified a negative being squared as just the positive being squared. And they factored. And in the denominator, they factored out a -1. Okay.
So does that -1 being factored out affect the numerator?
It will.
Okay.
It'll just change your signs in the numerator. But here, where I would, what I ended up factoring the sine minus the cosine, they're going to factor out the sine plus cosine. And dividing by -1. Well, they didn't show that step. You're dividing by -1, so the sine becomes minus and the cosine becomes plus. I think their way is a little more complicated. I would say dealing with the even odd identities until you got to the end or close to the end.
So to apply the even odd identities to the variant, is that what you're saying?
Yeah, because then you're changing the sign on sign and not on cosine, so it makes things a little more complicated. Dividing by one's a little more complicated than dividing by one. Simply because people have a tendency to forget that you're gonna change the sign of these two things. And so you can switch their order. So instead of sine minus cosine, it's cosine minus sine. So notice because they did it slightly differently than I did. Notice the fact that it does not necessarily matter the order in which you do certain things. So using the even odd identity did not affect the end result. It's just a slightly different pathway to get here than what I did. That's all.
Can you show what it looks like factoring out the negative one? I'm having a hard time.
Okay. So you have sine theta minus cosine theta divided by a negative one.
Okay, what-
Right?
Factor out the negative one?
Because this going away does not make the negative go away.
Yeah.
And we're always multiplying by one.
uh-huh.
So negative one remained in the denominator.
Oh, okay.
Okay. And so what I can do up here is I can divide negative one out of that. So negative one times a negative sine theta plus cosine theta divided by negative one, right? I just divided negative one out of each of these. So I could put a negative one on the outside. So this negative one over this negative one goes to one. And then I just switch my order here, so it looks like this. So, and they just did that from here to here. Because whether you're dividing by negative one or multiplying by negative, the end result is the same. You're changing your signs here. You're changing the order of the subtraction. And I did not get out myself. Now, use. And since I don't drink alcohol. I think I'll put that. And technically, I think it's illegal for me to drink alcohol on campus anyway. But I don't drink anyway, so. I'm not an alcohol drinker. I mean, I'll drink alcohol once in a while, but it's usually a year or two between drinks. My preferred poison is tequila. Anyway, the more expensive, the better, but which is another reason why I don't. Okay. Ha. All right, here. What would I do here? Oh. I can multiply, well, let's see, what are they gonna do? Okay, I see what they're doing. Okay, okay. So I either want the numerator to be in cotangent or the denominator to be in tangent. So cotangent is 1 over tangent. So I'm going to write my denominator as a single fraction. So 1 is tangent over tangent. So this becomes tangent plus 1 over tangent. Ta-da. So what they. So this one is the same as multiplying by tangent u over tangent u. So it's the same thing as adding tan u over tan u, because that's one. I just rewrote one to be something else that I can use. The denominators are the same, and I just add the numerators. Well, basically what I'm doing here, I'm dividing by a fraction, right?
Mhm.
That's the same as multiplying by its reciprocal. A lot of times I go through and explain why we do, when you're dividing by a fraction, why it's multiplying by its reciprocal. I don't do the cross multiply deal of dividing fractions because that's the only way I was taught to do it, and I got the wrong answer almost as often as I got the right answer. And this from a person who enjoys math. And so once I learned that it's multiplying by the reciprocal, and then I figured out why you multiply by the reciprocal, it made perfect sense. And I won't go through that explanation today, but yes. So I rewrote this dividing by this fraction to multiplying by this fraction. Well, now my numerator and denominator have the same factor. So this is just tangent of u. Well, why didn't I say that? There you go. So that's what they're going to end up doing. So I'm going to erase what I did here, and let's see what they do with it. Yeah. They multiplied by the reciprocal. So multiply the numerator by tangent, and the denominator remains tangent u plus 1, and these are the same value, so they go away and just leave you tan u. So they did the same thing without showing that they did the same thing.
So they multiplied the denominator by tangent so that the identities could be the same, right? So that way you can like cancel it out.
Well, yeah, one way of doing this is I multiply the denominator by the tangent of u, and I can multiply the numerator by the tangent of u. Because I'm multiplying by 1, here I'm multiplying a fraction by tangent of u, and here I'm just multiplying this expression by tangent of u. And these two tangents go to 1, which just leaves us to tan u plus 1 in the denominator,
Mhm.
which goes away with the 1 plus tan u in the numerator, which just leaves us the tangent.
Mhm.
So however you choose to do it, either multiplying numerator and denominator, and that's another way. This is a complex fraction, and the way to simplify a complex fraction is to multiply the numerator and denominator by the common denominator of these two things. The common denominator is tangent u. Right, because this is 1 plus tangent u over 1, and the common denominator here is going to be tangent u. So I would just multiply this by tangent u to get the same denominator. So multiplying both the numerator and the denominator by the common denominator gets rid of the fractions in the numerator and denominator. And that's probably what they did here to get this. So they multiply the numerator by tangent and the denominator by tangent to simplify the complex fraction. Sine over cosine. All right, so I want my denominators to be the same, so I'm gonna multiply this one by sine. The denominator by sine and this denominator by 1 plus cosine. Ha! So that means I'm gonna multiply the numerator by the same things. So I'm gonna multiply sine by sine and get sine squared theta, divide, and that's a plus sign. All right, now I'm on. Okay, yeah. I don't know why the computer decided to restart itself right in the middle of class. If it done it at 9:30, I would have just said, well, fuck it. Everybody could just go away now. Yeah, but yeah, we still got 40 minutes left of class, so. What? Yeah, now we got 30. Okay, so talking while I'm trying to type in a password is not always the best thing to do. I did it right. Okay. And there's the class. And let me get Zoom back up. I'm gonna get Zoom back up before I get everything else back up. And as soon as I get Zoom back up, I'm going to hear myself. Okay. Which one is me? Okay.
There you go.
On this device. All right, here we go. So, oh, I erased what I was doing. And so I'm multiplying numerator and denominator by sine. And so that gives me sine squared theta. And I'm just gonna write it as one fraction because I'm just gonna be multiplying these two together. So that's gonna be sine theta times 1 plus cosine theta. Plus, and now I'm multiplying 1 plus cosine theta by 1 plus cosine theta. 1 plus cosine theta times 1 plus cosine theta. All right, this one gets a little tricky, not too tricky, but a little. Because we have to multiply, we have to do the multiply. So I have sine squared theta in my denominator. I'm going to go ahead and write that down. Sine theta times 1 plus cosine theta. And now I'm going to do a binomial multiplication. 1 times 1 is 1 squared. 1 times cosine is cosine. And then cosine times 1 is cosine. And I'm going to combine those two to give me plus 2 cosine theta. And then cosine times cosine is plus cosine squared theta. Does anyone see it in the numerator? Does anyone see a trig identity in the numerator?
The sine squared plus cosine squared, which is
Right.
equal to 1.
Sine squared plus cosine squared is what?
Equal to 1.
Is equal to 1. So these two become 1, so it's 1 plus 2 cosine theta divided by sine theta times 1 plus cosine theta. Well, what's 1 plus 1? 2. So I don't even need, I could have just done that. I could have done that to begin with, right?
Mhm.
So now in my numerator, my two terms up here have 2 as a factor. So I can divide 2 out of both of those. So this becomes 2 times 2 divided by 2 is 1. And 2 cosine divided by 2 is just the cosine theta. Divided by sine theta times 1 plus cosine theta. Well, I have 1 plus cosine theta in both numerator and denominator, so those go to 1. So this just leaves me 2 over sine theta. What is 1 over sine theta?
Cosecant.
Cosecant. So this is 2 times cosecant theta, which is what we wanted to prove. Ba-dum boom. Now, I will very often, instead of writing this out in a big old long expression, I will multiply, when I'm multiplying two binomials, I'll do the product of the first and the last, and the product of the two insides. And I'll write them separate, and then I'll combine them and write the combined over here. Rather than making this all big long thing of doing it. I'm looking for this, I stared right at it. Walked away from it. Okay. So I'm gonna end up erasing this to see what they do. Whoops. Uh-oh. Uh-oh. Oh, I know the problem. There we go. The left side is more complicated. Hell yeah, it's more complicated. You're adding two fractions. And as far as trigger identities, there's nothing more complicated than adding two fractions together. And so they added them, which is what I did. They didn't show that they multiplied by sine over sine and multiplied by cotangent. I mean, 1 plus cosine over 1 plus cosine, but they did. And then they expanded that. They expanded it to this. All right, multiplied out in the numerator. And then the next thing to do is this goes away with that because they become one. Oh, they did the commutative property and put them together. Which a lot of people do. Regroup. Like that. Regroup. We're gonna regroup. Okay. And so here they did sine squared plus cosine squared is 1, and then they did the 1 plus 1. So they did that to begin with. Like I should have done. And then they factored out the 2. So they worked it exactly the same way I did. Factor and cancel. What do you mean cancel? They factor. They didn't factor and cancel. And it's not canceling. This is not canceling. Canceling implies 0. This is taking out I call it taking out the ones. Because 1 plus cosine over 1 plus cosine is 1, so I'm taking them out. So I'm taking out the 1. Mr. Sullivan, if we ever meet, we're gonna have an awfully long discussion. So, and then using the inverse, the reciprocal identity with sine, we get 2 cosine. So they did it the same way I did, but he used the wrong term.
I used to say that all the time too.
We're cancel, yeah.
No,
And
it's not cancel.
That comes from having elementary and middle school teachers teaching who don't understand the language of mathematics. My biggest pet peeve is having elementary teachers teaching students mathematics when they don't understand what they're teaching. Or they hate what they're teaching.
Have you seen the way they've been teaching it though? Like my niece, she went from like school to like homeschooling because of the way that they taught math. They were like, it was so weird. Like I'm really good with math sometimes. And I would help her and I'd be like, I don't know what to do. Like it's so weird. Like they use like lines or like they're still in 4th grade and they're still using lines to like math. And I'm just like, why? Like it doesn't make sense.
Using what?
Lines to like figure out the math. And I'm just like,
Like
Yeah,
the tally
I
marks.
understand.
yeah, like stuff like that.
Tally
Like,
marks.
mhm.
Like the
Tally
tally
marks?
Yeah, like the count with the tally mark.
I understand. When I taught at Mark Twain, I was at Mark Twain for 2 years. And the first year I was there, we went through 3 separate math programs. Somebody in the district, Dr. Long, was getting kickbacks. Dr. Long was the superintendent at the time. She was as crooked as a day is long. But anyway, she wrecked her car when she was off duty, like on a weekend or something, and she got the district to buy her a new car. Yeah. Anyway, there was other things going on. Anyway, I have rumors floating around in my head that are totally unsubstantiated. Although a friend of mine, his wife can verify it, but anyway. What was I gonna say here? God damn it. Oh, adding a -3 plus 5. Well, -3 can be thought as 3 negative signs. 5 can be thought as 5 positive signs, right? So the best way to understand this is 1 negative and 1 positive is a 0 pair. And so here I have 3 0 pairs. I don't have any more negatives. What's left over? +2. If they're both negative or both positive, then we're not concerned about this. But if it was 5 minus 3, then I would rewrite this as 5 plus a -3. Subtraction is addition. You just gotta keep the sign with the number. So it's the same deal. And so how I explain subtracting different numbers, different signs, you actually subtract the numbers. 5 minus 3 is 2, and you keep the sign of the one that has more. So there's more positive, the answer is positive. If there was more negative, then the answer would be negative. Anyway, I thought that was unique and novel in that program. And then by Christmas, we had moved on to another program. Okay, they're really screwy in that district. There's so much corruption and crime in that district. Taking money under the table. That it's systemic with it, and I don't know if they've gotten rid of it yet. Okay. I only worked for 2 years, so I really have no place to stay. All right, yeah. Interesting here. Well, I can write everything in terms of sine and cosine. Let's try that. Let's see what they did. Yeah. So they wrote everything in terms of sine and cosine. Tangent is sine over cosine, and cotangent is cosine over sine. What time is it? I don't want to know that Marcus, emails. Okay.
Why did they change it to sine and cosine? Like, is it simpler?
Because those are easier things to deal with.
Okay. So whenever we can, we should try to change it to sine and cosine?
Yeah.
If we can, okay.
Now, we can multiply everything by the common denominator. The common denominator is cosine times sine. Oh, damn, this just equals 1. Holy hell. Okay. And so let's go through their process. Okay. So they wrote the numerator is 1 fraction. So I multiply by sine over sine, and I multiply by cosine over cosine.
Oh, okay.
So I have the same denominator, and so my numerator becomes sine squared plus cosine squared, which is 1. And just multiplying here gives me cos, and so these go away, so I just have 1 over 1. Cool, that's awesome. Okay, so now they go through and they say that the numerator is 1 over cosine times sine. Right, so they made that 1, and then they changed dividing by a fraction by multiplying by its reciprocal. And here we have cosine sign in the numerator and cosine sign in the denominator. Those go to 1. And so it just equals 1. All that work for 1. In one of my classes in high school, I can't remember which one it was. I don't know, it may have been when I was in Pierce Hall, I can't remember. We worked this problem out, and the answer equals 0. And it was a big old long process, and we got 0 at the end, and the student popped up in the back, said, all that work for nothing? It went over big in the class at the time because. But this is cool. I like this one. Yeah, oh, well, I knew we were gonna get, I should have known we were gonna get to 1 anyway. I didn't even look at this side. I just looked at, well, what changes can I make? Any questions here on this one?
It looked really hard at first, but
The problem here is you're gonna be forced to deal with fractions. And the more you understand how fractions work, the easier these things become. Because right here, because the denominators of the two things in the fraction are the same, those could have gone to 1 right then. Because that's like 1/2 divided by 1/2. Well, that's just 1/1. Or 1. Which is what we have in this case. All right. Let's see what they do. I have thoughts in my head what I could do here, but start with the left side, multiply the numerator and denominator by 1 plus sign. Yeah, so then we would get 1 minus sine squared in the numerator. So what they're saying here inside the parentheses is that they could attack this side to make it look like that side by multiplying the numerator and denominator by 1 minus sign. Because we're going to multiply by 1 plus sign, so this becomes 1 minus sine squared. Divided by cosine times 1 plus sine. Right, please notice that they're not going to multiply in here. Because we're going to get something that'll factor out. Because what is 1 minus sine squared? Cosine squared. Think of the Pythagorean theorem or the Pythagorean identity. So we have cosine squared over 1 plus sine. So I have cosine squared being divided by cosine. So that means this cosine is going to go away with one of those cosines. Which means we're left with what is on the right-hand side of the equation up there. Cancel. No, we don't cancel. God damn it. Oh, that's gonna bug the ever-living daylights out of me.
sometimes you have to let things go.
Yeah, I know, but still. But this is a professional document. It shouldn't have those kinds of mistakes in it.
You should email them.
It should be simplified. Or reduce the fraction, not cancel. When you cancel a TV show, it goes away, yeah, but it's gone forever for a different reason than this is going away. It's still there, it's 1/1, it's one is still there. Okay. It's almost always preferable to start with the side containing the more complicated expression. And the side with the more complicated expression is usually the left-hand side. Rewrite sums or differences of quotients as a single quotient. Sometimes it helps to rewrite one side in terms of sine and cosine only. Always keep the goal in mind. As you manipulate one side of the expression, keep in mind the form of the expression on the other side. Okay, so you're always looking to see, well, how can I get rid of these and put that in? Okay, so sometimes writing everything as sine and cosine. And then when you get closer to the end, you can rewrite it back again. So if it doesn't contain sine or cosine on the other side, then there are ways to change it back again to make it look like what you need. Okay. And sum and difference formulas. Oh, these are. Use sum and difference formulas, find exact value. Use sum and difference formulas to establish identities. Use sum and difference formulas involving inverse trig functions and using and then solving trig equations linear in sine and cosine. I'm thinking they mean to say linear trig functions. I think the linear is supposed to be over here. Okay. And I'm gonna leave it at this, and we're gonna start with this next time. But suffice it to say, well, the formulas for cosine and sine, the sum and difference, are similar, but they're different enough to cause massive confusion. Okay, so, and this is lowercase alpha, and this is beta. Again, with the Greek letters, the Greek alphabet. The cosine of alpha plus beta is cosine alpha, cosine beta, minus sine alpha, sine beta. So if you're adding the two angles, it's going to be subtracting the two products. And if you're subtracting the two angles, it's going to be adding the two products. And with cosine, it's quite simple. It's going to be cosine, cosine, plus or minus sine, sine. The tricky part is with sine, because it's sine, cosine, and sine alpha, sine cosine, and sine alpha, cosine beta, and then sine beta, cosine alpha. So that's where the confusion can come into play. With cosine, it's quite simple. It's just keeping track that if you're adding the two angles, you're subtracting their products. The products, and if you're subtracting the two angles, you're adding the two products. So next, no. Oh. So 105 degrees is the same as 45 plus 60. I know the cosine of 45 and the sine of 45. I know the cosine of 60 and the sine of 60. So we use the formula, we're adding here, so we're going to subtract the two products. And so it's going to be cosine 45 times the cosine of 60 minus the sine of 45 times the cosine of, oh, that should be sine here. Fucking assholes. So the cosine of 45 is pi over 2, I mean square root of 2 over 2. The cosine of 60 is 1/2. The sine of 45 is square root of 2 over 2. And the sine of 60 is the square root of 3 over 2. And so we get, well, I would have written the answer different than they did. I would have left it as a fraction. Because what happens here is, yeah, we're at time. So I'm just going to show you what I would do here. This would be the square root of 2 over 4 minus the square root of 6 over 4, which is the square root of 2 minus the square root of 6 over 4. I would have written it this way and not that way. When you're multiplying two square roots, it's just going to be the square root of their products of the radicals. And unless you have questions for me, y'all can go.
Thank you. We'll see you Monday.
All right, and I apologize for the computer crapping out on us. Right in the middle of class.
Monday is Columbus Day, so we're not gonna hear it.
Oh, we're here.
Oh, okay.
Yeah.
Have a great day. Take care.
You too.
Thank you.
Yeah, the only holidays we have are, well, the next holiday is Thanksgiving.
Thanksgiving, okay.
Thank you.
So, yeah.
Excuse me, sir. Excuse me.
Yes.
I had a question. When is our next exam?
The end of this month, I can't remember the exact date.
Oh, okay, okay.
It should be in the syllabus.
October 27.
Okay,
What? Oh, the 27th?
Yeah.
all right.
So the last Wednesday of the month.
Okay, thank you.
So let me go here and close that down. I'm going to go ahead and end the meeting. And